For more than 4,000 years, one structure has refused to give up all its secrets. It has survived earthquakes, empires, looters, and the slow grinding pressure of time itself. And yet, in the last few years, something happened that even the scientists who found it struggled to fully explain. Deep inside one of the most studied monuments on the planet, a monument that has been measured, mapped, and photographed more times than almost any other building in human history, researchers detected something that should not have been there. Not a myth, not a rumor. A real physical anomaly, confirmed by multiple independent scans, sitting quietly behind solid granite, exactly where nobody expected to find anything at all. This is the story of how that discovery happened, why it is so hard to explain, and what it might mean for everything we thought we knew about how the pyramids were built. To understand why this find matters, you have to understand just how much attention the Giza Plateau has already received. Generations of archaeologists, engineers, and explorers have crawled through these structures with torches, ropes, and increasingly advanced equipment. The Great Pyramid of Khufu alone has been surveyed with lasers, penetrated with robots, and scanned with cosmic ray detectors. By the 21st century, most experts assumed that if there were any major hidden spaces left inside these monuments, they would have been found decades ago. That assumption turned out to be wrong. The story really begins to accelerate in 2017, when an international team working on a project called Scan Pyramids used a technique borrowed from particle physics to peer through solid stone without drilling a single hole. The method relies on muons, tiny subatomic particles that are constantly raining down on Earth from collisions high in the atmosphere. Muons pass through solid rock in enormous numbers, but they are absorbed at different rates, depending on the density of the material they pass through. By placing sensitive detectors inside and around the pyramid and recording how many muons made it through from different angles, the team could essentially build an X-ray image of the interior, revealing dense stone as one kind of pattern and hollow space as another. Using this approach, the Scan Pyramids team identified a large void above the Grand Gallery inside the Great Pyramid, a space that had never appeared in any historical record, any medieval account of tomb robbers, or any modern excavation report. It was, by any measure, a genuinely new discovery inside a building that people had been investigating for well over a century. That first void was strange enough, but the story did not end there. In 2023, using a combination of muon tomography, endoscopic cameras, and ultrasonic testing, researchers confirmed a hidden corridor near the original entrance of the Great Pyramid, tucked behind the chevron-shaped stones on the north face. This corridor had likely been built as part of the structural design meant to redistribute weight around the main entrance, but its existence had simply never been documented before. For a building that millions of tourists visit every year, and that has been the subject of nonstop academic study since the 1800s, finding a completely unknown internal feature is remarkable. It proved that even the most examined structure on Earth could still contain surprises, and it set the stage for what came next. That next chapter unfolded not in the Great Pyramid of Khufu, but in its smaller, often overlooked neighbor, the Pyramid of Menkaure. Menkaure's pyramid is the smallest of the three major pyramids at Giza, and for most of the last century, it has lived in the shadow of its larger siblings. The last serious archaeological exploration of its interior had been carried out by George Reisner in the early 20th century. Since then, almost all of the scientific attention at Giza had gone to Khufu's pyramid, leaving Menkaure relatively unexamined by comparison. That changed when a team of researchers decided to apply modern, non-invasive scanning technology to its eastern face, an area that had been largely neglected compared to the pyramid's northern entrance. Using ground-penetrating radar, a method that sends radio wave pulses into a structure and measures how they bounce back based on what they hit, the team scanned the eastern side of Menkaure's pyramid. What they found were two distinct anomalies, located directly behind a section of polished granite blocks. The pattern in the radar data was consistent with what scientists describe as air-filled voids, meaning there appeared to be genuinely empty space hidden behind that granite facade, not just a shift in material density or a natural fracture in the rock. The team published their findings in the scientific journal NDT and E International, and they were careful to stress that their scanning method had no physical impact on the structure itself. No drilling, no cutting, no risk to the pyramid, just radio waves passing through stone and returning information about what lay beyond it. What makes this discovery genuinely difficult to explain is not simply that a void exists. Ancient buildings settle, shift, and develop small gaps over the centuries, and archaeologists know how to identify those kinds of natural imperfections. What stood out here is the position and consistency of the anomalies. They sit directly behind carefully placed polished granite blocks in a location that had long been treated as a neglected secondary side of the monument. Polished granite was an expensive, labor-intensive material for the ancient Egyptians to produce and transport, and it was typically reserved for significant architectural or symbolic purposes, not just decorative filler. The fact that hidden voids sit precisely behind this kind of deliberate stonework suggests that this was not an accident of construction or a random gap left by settling stone. It points toward intentional design, a purpose-built space that the pyramid's original architects planned for, then sealed away and left undocumented for over 4,000 years. Researchers have floated a few possibilities for what these voids might represent. One leading idea is that they could mark the location of a second entrance into the pyramid, mirroring the way multiple entry points and internal corridors have already been found in the Great Pyramid of Khufu. If that turns out to be correct, it would mean that Menkaur's pyramid, long assumed to be structurally simpler than its larger neighbors, may actually contain an internal layout far more complex than anyone previously mapped. Other researchers have suggested the voids could relate to ritual practices tied to the pyramid's original function as a royal tomb, spaces built not for practical access, but for symbolic or religious reasons that were significant to the builders, but remain opaque to us today. As of now, no camera has been sent inside to confirm which explanation is correct, which is exactly why this discovery is described as hard to explain. The data is solid, the interpretation is still open. This uncertainty is actually one of the most honest and important parts of modern pyramid research. It would be easy to leap straight to a dramatic explanation, but responsible archaeologists are resisting that urge, choosing instead to treat this as a lead that requires further physical verification before any conclusions are drawn. That kind of caution matters, especially because pyramid archaeology has a long history of being distorted by sensational claims that outrun the actual evidence. To understand why that caution is so important, it helps to look at a separate story that made headlines around the same period, involving claims of a vast underground city hidden beneath the Pyramid of Khafre, the middle-sized pyramid at Giza. A team of Italian researchers announced that their radar surveys had detected not just a chamber or two, but an entire network of tunnels and hidden spaces beneath Khafre's pyramid, describing it in terms dramatic enough to suggest an underground city. The claim spread quickly, fueled by exactly the kind of appetite for mystery that surrounds ancient Egypt. But independent experts pushed back almost immediately. A radar specialist at the University of Denver publicly stated that no form of ground radar currently available is powerful enough to penetrate the deep beneath the Giza plateau with the kind of resolution needed to map an entire underground city. He acknowledged that smaller features, like wells or isolated chambers, might genuinely exist and be detectable, but he was clear that the dramatic underground city interpretation went well beyond what the technology could actually support. This story is a useful contrast because it shows what happens when a claim is stretched past what the evidence can bear, and it highlights exactly why the Menkaur findings, which were published through peer review with careful, measured language, deserve to be taken seriously without being exaggerated into something they are not yet proven to be. A similar cautionary example comes from far outside Egypt in Indonesia, where a site called Gunung Padang became the center of an international debate, after a research team claimed it might be the oldest pyramid ever built by humans, with construction potentially beginning more than 20,000 years ago. If true, this would completely rewrite the known timeline of advanced human construction, placing it thousands of years before even Egypt's earliest pyramids and before the famous megalithic site of Göbekli Tepe in Turkey. The claim rested on carbon dating of soil found between layers of stone extracted from a drilled core sample. But critics, including several respected archaeologists, argued there was no clear evidence that the deepest layers were actually built by human hands, rather than shaped naturally over time by rockfall and erosion rolling down the hillside. This dispute remains unresolved, but it illustrates an important pattern. Whenever a pyramid-related claim generates global headlines, it eventually gets tested against rigorous scientific scrutiny, and only the claims built on solid, reproducible evidence survive that process. Which brings the story back to Egypt, and to a second major discovery that has quietly reshaped how scientists understand pyramid construction itself, separate from what lies inside these buildings. For centuries, one of the biggest unanswered questions about the pyramids was not what secrets they might hide internally, but how the ancient Egyptians managed to move millions of massive stone, blocks across the desert, to build them in the first place. The Great Pyramid of Giza alone is made up of roughly 2.3 million stone blocks, each weighing between 2.5 and 15 tons. Moving that much material by hand across dry desert terrain using only Bronze Age technology has puzzled engineers and historians for generations. Various theories were proposed over the decades, ranging from wooden sleds to elaborate ramp systems, but none of them fully explain the sheer logistical scale of the operation. A research team led by Dr. Emin Ghonem at the University of North Carolina, Wilmington approached the problem differently. Instead of focusing on the pyramids themselves, they focused on the landscape surrounding them, using satellite imagery combined with radar data capable of detecting features buried beneath desert sand in modern farmland. What they found was the ghost of an ancient waterway, a now buried branch of the Nile River stretching roughly 64 kilometers, or about 40 miles, running along a path that borders 31 different pyramids, including the Great Pyramid of Giza itself. Researchers named this lost waterway the Ahrimat Branch. Its existence had been suspected for years, since ancient Egyptian texts occasionally referenced waterways near construction sites, but nobody had definitively located or mapped it until this study combined satellite data with sediment analysis and other archaeological indicators to confirm its path. This discovery matters enormously because it finally offers strong physical evidence for how these enormous stone blocks were actually transported. If a major branch of the Nile once flowed directly alongside dozens of pyramid construction sites, it would have provided a natural, efficient highway for moving heavy materials by boat, rather than dragging them for miles across open desert. It also helps explain why the pyramids were built in their specific locations. Ancient builders were not choosing random points in the desert. They were positioning these massive monuments along a working transportation corridor that made large-scale construction logistically possible in the first place. Over the following centuries, as the regional climate shifted and became drier, and as the flow of the Nile gradually changed course, this branch silted up and disappeared beneath layers of sand and farmland, erasing it from the visible landscape, and eventually from historical memory as well. Taken together, these two lines of research, the internal scanning that revealed hidden voids inside Menkaur's pyramid, and the external mapping that revealed a lost branch of the Nile running past 31 pyramids, represent two of the most significant advances in pyramid research in recent memory. One helps answer questions about what these structures might still be hiding inside them. The other helps answer questions about how they were physically built in the first place. Both were made possible not by lucky discoveries or shovels striking stone, but by scientists applying modern, non-invasive imaging technology, whether that meant ground-penetrating radar, muon detectors, or high-resolution satellite data, to a landscape and a set of buildings that people assumed had already given up everything they had to offer. That is really the deeper story here. It is not simply about one mysterious chamber or one buried river. It is about how much can still be learned from a subject that seems, on the surface, to be completely exhausted. Archaeologists have been studying the Giza pyramids for well over 200 years using increasingly sophisticated methods, and yet, within just the last decade, they have uncovered a previously unknown internal corridor, a large unexplained void, a set of anomalies suggesting a hidden internal chamber that may still be sealed today, and an entire buried river system that solves one of the oldest engineering mysteries in human history. Each of these discoveries came with careful scientific verification, peer-reviewed publication, and importantly, honest acknowledgement of what remains uncertain. Nobody involved in the legitimate research is claiming to have found treasure rooms, secret pharaonic archives, or evidence of ancient aliens, despite what more sensational corners of the internet might suggest. What they are reporting, cautiously and precisely, is that solid stone structures assumed to be fully understood are still concealing physical spaces and answers that modern technology is only now capable of detecting. So where does this leave the central mystery that started this whole story? The hidden voids behind the polished granite on the eastern face of Menkaur's pyramid. As of now, those spaces remain sealed. No endoscopic camera has been threaded through to confirm exactly what lies inside. No physical excavation has been approved to open that section of the structure. The radar data is clear enough to confirm that something is there, air-filled, space where solid stone should be, sitting in a location too deliberate to be dismissed as coincidence, but not clear enough to say definitively what that space was built for. That gap between confirmed detection and confirmed explanation is exactly why this story continues to generate so much attention. It sits in that rare, genuinely uncertain space between established fact and open question, the kind of space that used to be common in archaeology a century ago, and that modern technology was supposed to have mostly closed. Instead, the opposite seems to be happening. The more precisely scientists are able to scan these ancient structures, the more previously invisible features they continue to find. Every new tool, whether it is cosmic ray detection, ground-penetrating radar, or satellite-based landscape mapping, seems to reveal another layer of complexity that earlier generations of researchers, working with far more limited equipment, simply could not access. It raises a genuinely open question about how many more of these hidden spaces might still exist, not just within the Menkaur and Khufu pyramids, but within the dozens of smaller and less studied pyramids scattered across the Giza Plateau and beyond it, many of which have never received anywhere near the same level of scientific attention. What happens next depends largely on further physical investigation. Researchers involved in the Menkaur discovery will likely seek approval to insert a small camera through a narrow drilled access point, similar to the method used to confirm the hidden corridor inside the Great Pyramid back in 2023. If that happens, and if the camera reveals something concrete inside those voids, it could represent one of the most significant internal discoveries at Giza in over a century. If the space turns out to be structurally functional rather than symbolically significant, it will still meaningfully update our understanding of how these tombs were engineered. Either outcome adds real, verified knowledge to a subject that many people assumed had nothing left to teach us. For now, what can be said with confidence is this. Modern imaging technology has confirmed the presence of deliberately placed, air-filled voids behind polished granite on the eastern face of the Menkaure pyramid, a section of the monument that had been largely ignored by researchers for over 100 years. Separately, and just as significantly, satellite and radar analysis has confirmed the existence of a 64-kilometer branch of the Nile River that once ran alongside 31 pyramids, offering the clearest physical explanation yet for how ancient Egyptians transported the enormous stone blocks used in their construction. Both findings came from rigorous, peer-reviewed research. Both remain areas of active, ongoing investigation, and both are reminders that even a monument as thoroughly examined as the Great Pyramid of Giza and its neighbors can still surprise the people who have spent their entire careers studying it. It is also worth pausing on just how strange it is that ground-penetrating radar was even able to see through polished granite in the first place. Granite is one of the densest, hardest building materials the ancient Egyptians had access to, which is exactly why it was reserved for the most important structural and symbolic elements of their monuments. It takes a real technological leap to send a radio pulse through a slab of solid granite, have it strike an air pocket on the other side, and bounce back with enough clarity to distinguish that pocket from solid rock, all without drilling a single hole. A few decades ago, this kind of detection simply was not possible with any reasonable degree of confidence. The fact that researchers can now do this from outside the structure, without touching the stone itself, says as much about how far scanning technology has advanced as it does about the pyramid itself. This also explains why muon tomography, the method used to first detect the void above the Grand Gallery, has become such a valuable tool for archaeologists working on massive stone structures. Unlike ground-penetrating radar, which sends a signal into the structure and waits for reflection, muon detectors are essentially passive. They do not send anything into the pyramid at all. They simply sit and count naturally. Occurring particles that are already falling from the sky and passing through the stone on their own. Because muons lose energy differently depending on what they pass through, dense solid rock will absorb more of them than an empty space will. By comparing how many muons arrive at detectors placed in different locations, researchers can essentially build a density map of the pyramid's interior, similar in concept to a medical scan, but using cosmic radiation instead of X-rays. This method was first proposed for pyramid research decades ago, but it took until sensitive, portable detector technology matured for it to become practical inside an actual archaeological site. Its success at Khufu's pyramid is part of what encouraged researchers to expand similar, non-invasive scanning efforts to other structures at Giza, including Menkaure's pyramid. It is also important to place these discoveries within the broader context of how much the Giza Plateau has already given up over the past century, because that history is part of what makes new finds so significant. Beyond the pyramids themselves, researchers working across Egyptology have increasingly applied modern forensic and statistical techniques to material recovered from ancient tombs, studying skeletal remains to better understand the health, ancestry, and daily lives of people who lived thousands of years ago. These kinds of studies are a reminder that pyramid research is not only about architecture and engineering, it is also about the people who built these structures, the workers who moved stone along the Ahramat branch, the officials and rulers who were eventually buried within them, and the broader society that organized itself around a task as immense as constructing a mountain of stone by hand. That broader context also helps explain why researchers are so careful not to overstate what a discovery like the Menkaure anomalies actually proves. Egyptology as a field has been shaped, for better and for worse, by more than 2 centuries of competing claims, some rigorously supported by evidence, others driven by speculation, showmanship, or a desire to attach dramatic meaning to ordinary archaeological findings. The scientists behind the Scan Pyramids project and the Menkaure Radar Survey have consistently published their findings through formal peer review in scientific journals, where other experts can examine their methods and data before anything is presented as fact. That is a meaningfully different approach from the underground city claims at Khafra or the disputed pyramid claims out of Indonesia, both of which generated far more public attention than their evidence could actually support. The lesson embedded in all of these parallel stories is the same. Advanced technology can reveal genuinely new information about ancient structures, but it still takes careful, patient, peer-reviewed science to figure out what that information actually means, and that process is often slower and less dramatic than the headlines that eventually get written about it. There's also a practical reason why these discoveries are emerging now rather than decades ago. Ground-penetrating radar, muon detectors, and high-resolution satellite imaging have all become dramatically cheaper, more portable, and more precise in recent years, largely due to advances originally developed for entirely different industries, including medical imaging, resource exploration, and remote sensing. Archaeologists have increasingly been able to borrow and adapt these tools for their own purposes, applying industrial-grade scanning, equipment to problems that once could only be approached with a shovel, a notebook, and a great deal of patience. The Ahrimat branch, for example, would have been essentially impossible to detect using traditional excavation methods, since it lies buried under layers of sand and modern farmland stretching across a huge area. It took satellite radar capable of penetrating the ground, combined with sediment analysis at specific points along the suspected path, to confirm that a river once flowed exactly where the data suggested it should. This kind of multi-layered, technology-driven approach represents a real shift in how pyramid research is conducted, moving away from isolated digs toward large-scale, non-invasive surveys that can cover entire landscapes at once. None of this diminishes the significance of what has been found. If anything, it makes it more remarkable. These are not accidental discoveries stumbled upon by chance. They are the direct result of scientists deliberately applying the best available technology to some of the oldest and most heavily studied structures on the planet and still finding meaningful new information. That combination, rigorous method paired with genuinely surprising results, is exactly what makes stories like the Menkaure Voids and the Ahrimat branch so compelling, and exactly why they continue to be difficult to fully explain even after publication. The data is real, the methods are sound, but the final answers, the ones that would tell us definitively what those hidden granite chambers were built for, are still waiting somewhere on the other side of that stone. 4,000 years after the last stone was set in place, the pyramids of Giza are still not finished telling their story. And the next chapter of that story may already be sitting there, sealed behind granite, waiting for the right camera on the right day to finally see what is inside. If a discovery like this fascinates you, this is really just the beginning. Researchers are still analyzing the Menkaure data, and new scans of other pyramids across Egypt are already underway. If you want to be here when the next hidden chamber is confirmed, or when that camera finally goes through the granite, make sure you're subscribed, because this story is far from finished. And if you learned something new today, leave a comment telling me which discovery surprised you the most, the sealed chambers, or the buried river that built the pyramids. Hit like if you want more stories like this one, and I'll see you in the next video.